Welcome back, and in this video we will discuss the importance of determining the internal forces anywhere along a structural member such as a beam. We often see beams like these ones here with a free body diagram showing positive and negative internal forces. The idea of this introduction is to simply demonstrate the importance of understanding the evaluation process of these forces and how they can be useful in our day-to-day design. So what are the internal positive and negative forces in a beam? Well, consider we have a simply supported beam with a UDL and it has a length L. Then you know straight out that due to the external transverse loading, we will obtain a positive internal bending moment throughout the length of the beam, as you can see here in the bending moment diagram. We will also see internal positive shear force to the left half of the beam and negative shear force to the right half of the beam. I guess this is so far so good. So the idea now becomes, how do we calculate the internal moment and shear forces anywhere along the beam, as well as determine the exact sign convention? Okay, if we cut the beam at any distance, say a distance x, and then if we put a person looking to the left side of the beam, this looks like a funny duck face. I don't know what I've done here, but yeah, anyhow, this duck face, what will he see? Well, he'll see the following. He'll see a bending moment anti-clockwise, which causes compression at the top of the beam and tension at the bottom of the beam. Shear force down and normal force to the right. That normal force will cause tension to the right. And remember, we will see these internal forces as the beam is deforming due to the external loads. If there are no loads on the beam, then obviously we will not see any internal forces. Unless, of course, we have pre-stressed or post-tensioned concrete beam, then it's a little different. It's a different topic, and we can cover that in another video. Okay, if this same person turns their head the other way around and looks at the right side of the beam, they will see equal and opposite forces. Clockwise moment, which still causes compression at the top of the beam and tension at the bottom, shear force up, and normal force to the left. And this is what we call internal positive sign convention. And of course, if we don't have any external horizontal forces, then the internal normal force Nx would just be 0. The internal negative sign convention is obviously the complete opposite to the positive sign convention. I have written it here for you. So the complete opposite. Tension is going to be at the top of the beam and compression is at the bottom of the beam. That's due to the moment. Normal force NO is now inwards in compression. Shear force is now upwards at the left side of the cut, and the shear force would then be downwards at the right side of the cut. Now, you might be wondering, why in the world are all of this important? Why is it important for me to look at internal forces and internal moments and so forth? Well, many times we become interested to study the internal bending and shear stresses at a particular distance along the beam. And to determine the normal bending and shear stresses, we obviously need to first work out the values of the internal moment and internal shear forces. Okay, so let me show you some real-life examples of what I mean. The first example is a chamfered beam, and this is very common. Say we have a beam with transverse loading, and we need to chamfer the ends of the beam on an angle, as shown here. Then we would need to be interested in the stresses at the junction of the chamfered area. Of course, shear stresses at the ends would be more critical. However, as we move towards the right side, the length of the beam, we will also experience bending stresses. And if you notice in this example, we may also have normal force NX as well. Why do you think that may be the case? Well, because we have a chamfered beam on an angle, and so the external loads acting normal to that angle surface would then need to be resolved into an external vertical and a horizontal force. So if we take a free body diagram around the chamfered section, then to the left of the cut we have shear force down, bending moment anti-clockwise, and normal force to the right. So assuming that duck face person is looking to the left of it, this is what he will see. Now these forces are the resultant of the stresses acting on the face of that little trapezoidal section. Then on the right side of the cut, we will have equal and opposite forces. So in this case, we will have shear force up, bending moment clockwise, and normal force to the left. And they will be the resultant forces on the rectangular face of the beam. Once we determine these forces, then we can work out the applied flexural and normal stresses and compare them to the allowable stresses of the beam material. At the end of the day, stresses and deformation are the main criteria to help us know if the beam has passed or failed. Okay, another example, a second example could be a small cutout anywhere along the beam length. This is very common as well. In this case, we may need to take more like 3 free body diagrams to work out the internal stresses on each face of this cutout. So here we have to look at 3 individual parts. The left side, on the full depth of the section, we have anti-clockwise moment, shear force down, and normal force outwards. Then looking at the right side of the cut, we have equal and opposite forces, clockwise moment, shear force up, and normal force tension to the left. Then again, looking at the left side of the cut, of that little cutout, well, depending on how long this cutout is, we may get an additional change of moment and shear. So we should be really writing this side as M plus dm plus an additional moment and V plus dV. In any case, assume it's a very small cutout, then we will see equal and opposite forces. So that would be, moment anti-clockwise, shear force down, and normal force to the right. And the story goes on and on and on, as you guys can see here. So hopefully you got the idea of what I'm trying to get at. The last example, which is common, is a hole in beams. Look, there are many examples out there, but these are the 3 main ones I can think of. So this is exactly the same idea as the beam cutout that we spoke about before. We take 3 free body diagrams and draw in the internal forces and show as shown below. Here we have 3 parts and the internal forces to the left and to the right of each cut as shown. So this simple method of understanding the load path of internal forces in the beam structure due to external loads helps us to effectively design the beam and work out the applied and allowable stresses. In the next video, we will go through a numerical example and we will hopefully show a step-by-step process of how to calculate internal forces for a given beam geometry and external loading. So we hope you enjoyed this video, and if you have found it useful, please subscribe, share and like our channel. Until then, we hope that you have a great afternoon.